All right, so this problem deals with resistors and capacitors in circuits and some of the properties as current flows and stops flowing as capacitors charge. So part A is calculation-ish, right? You don't have numbers, but you can set up a relationship between the variables by plugging in what you know. So first thing I'm going to do, when I have a circuit question, I want to really be able to visualize the circuit, so I'm going to draw it. Right? You have four components in the series, right? So it's a pretty simple circuit. And we have the battery, a resistor, a capacitor, and a switch, right? And so capacitance C, resistance R, EMF E. Okay. So, initially, the capacitor is uncharged. So, we close the switch. This circuit behaves as if the capacitor is not there at all, right? Because there's no charge stored on it. So that means that there's no resistance to flow across it, right? There's no charges to sort of exert a repelling force on more charges, right? So initially your circuit really just looks like that. And so we want the potential difference, we want the current across the resistor. So delta V equals IR, and I equals delta V over R, but delta V is just what the battery provides, right, from the loop rule. So that's epsilon over R, right? So that's that part. That's pretty straightforward. And because there's no charge on the capacitor, right, delta VC equals 0 volts, right? This one didn't ask for explanation, so you can stop right there. You don't need to explain any more detail. Alright, so now we have the same thing after a long time. So after a long time, the capacitor is now fully charged. And fully charged means that no more charge can flow. And so this behaves just like a broken circuit. Right? And so at this point, because it's broken, no charge can flow. So I equals 0, right? By definition, no charge is flowing. That's what long time means in the sense of capacitors. But Kirchhoff's loop law still must be true. If there is 0 current, that means there is 0 potential difference across this. So delta VC then must equal delta V battery, or the whole, right, epsilon value. Right? Kirchhoff's loop law still works. All right, so that's part A, hopefully fairly straightforward. Drawing the pictures really does help. So now we're changing something. We reset our circuit back to the exact original state, right? So we have our battery, our resistor, and our capacitor. Then we put a new capacitor in, right, in series. Oops. Right, and there's our switch. So we put it like this, and we say, okay. Now, when we close this switch, how does the energy stored here, this is energy 2, how does this compare to the energy that we stored before? Right, these capacitors are identical. So there's two different ways you can approach this. Because they're identical, after a long time, we know that this is epsilon over 2, and this is also epsilon over 2 of potential difference, right? They're identical, so the potential difference across them has to be the same. The other way to approach it is to combine these capacitors into one, right? Where we have one sort of better capacitor, where this C, right, the capacitors in series are the inverse relationship. So I'm going to call this one C prime, right, to indicate that it's not C, is going to be C over 2. If you do that 1 over C plus 1 over C inverse, right, you get 2 over C inverse, which is C over 2, right? And then this one has delta V equals epsilon, right? Because there's just one capacitor. Either way. And so we can calculate U2. In either case, it's exactly the same, fortunately. So U2 is 1/2 C delta V squared. Actually, I should just write that as that's the energy stored in the capacitor. And now if we plug in what we know, 1/2 C over 2 epsilon squared, right? If you do it with the two capacitors approach, you have two terms. Each one contributes half of this total value, so it's going to have to be the same either way. So U2 equals 1/4 C epsilon squared. And the original energy, right, is simple. It's 1/2 C epsilon squared. So U1 over U2 is 1/2 C epsilon squared, 1/4 C epsilon squared. A lot of stuff cancels, and we're left with 2, right? So that's B part 1. Now, B part 2, depending on how you approached it, either with this top approach or this bottom approach, might take you either a little bit more time or not very much at all. So the key is to recognize that this relationship, right? The two capacitors that store the same energy, the one capacitor that stores the same energy as the two capacitors must have 1/2 of the capacitance. So our new capacitor has got to have C prime equals C over 2. Okay, now we have to remember, what do we know about how to calculate the capacitance? Well, the capacitance in general is epsilon naught A over D. So if we need to make this thing 1/2 what it used to be, we have two different options. We can either A to A over 2, right, make the area half as big, or D to 2D, right, make the plates twice as far apart. And so you should, in solving this, you should reference this equation, reference this change, and then make sure you explain in words what this means, right? This area A is the surface area of the plates. This distance D is the spacing between the plates, right? So that's kind of how you should answer that. All right, and then finally, part C is the part that may either be really, really fast or take the most time, I think, because you've now been thinking about capacitors and resistors in combinations. So hopefully you've kind of got your mind guided the right way, but this one gives you less sort of structure to it. So we have two goals, and we need to make a circuit that meets those goals. So in circuit 1, we need the light to sort of start off dim and become bright. In arrangement 2, we need the bulb to be bright and start out dim. And I think arrangement 2 is actually easier to start with, because arrangement 2 is actually what you already did in part A, right? Right, resistors, light bulbs are resistors. So if we make a circuit that looks exactly like the one that was described in part A, right, this is now a light bulb instead of just a general resistor. Right, what will this do? Well, initially, we have current I flowing through it. Eventually, the capacitor fully charges and we don't have any more current. Right, so since the power is I squared R, and that's sort of like the brightness, then this will start off bright and end up dim. Right, so this is arrangement 2. And so hopefully when you do that, you think, well, what other options do we have? Series makes it start off bright and end up dim, so maybe try parallel to see if it makes it do the opposite. Let's see if that actually happens. Because there's only two different ways you can combine things, right? Either in series or in parallel. If I put more capacitors in series, it doesn't change the sort of short-term and long-term patterns, it'll just change some of the numbers. So we need to do something completely different. The only way to do that is trying the other way of combining the stuff. Right? Okay, so there's our light bulb. So now let's think about what happens. Right? And so I'm going to draw initially I'm going to draw that in blue, and long time will be in red. So initially, what happens? The capacitor essentially is like a short circuit. So all the current goes through the capacitor. Because the light bulb has some resistance, and until the capacitor gets any charge at all, the capacitor doesn't have any. So all the current initially will go through the capacitor path. So initially, I equals 0. What about after a long time? Well, after a long time, the capacitor is fully charged. Now it's like the circuit is broken. It's like it's not even there. And so all the current will now go through the light bulb. Which means after a long time, the current is a maximum value, whatever that might be, based on exactly how much resistance the light bulb has. It doesn't matter, it's definitely a maximum. And so this one will work. So this has to be arrangement 1. Right? So I've kind of talked through the paragraph that you need to write about. Basically, the idea is to describe what the current looks like, both initially and after a long time for both of these configurations, and then connect the current to the power or something else to show that the current determines how bright the bulb is. Right? And if you do those things and properly label and draw the arrangements, then you get the points.